Example problem number 3. Looks like a hits the wall problem. This is the first of our 2 hits the wall problems. This one's about a baseball hit. We're given an initial velocity v naught. V naught is equal to 37 meters per second. Angle theta is equal to 35 degrees. Okay, here's the idea. We have a baseball that's hit and 124 meters away. We have the wall. Let's make it look more like a wall here for a second. All right, now it's a wall. All right, so what we want to do is we want to see if this baseball will clear the fence whose top is 5 meters above where the baseball was struck. So in other words, will the baseball, I'll make green for go, will the baseball go, or will the baseball, red, stay? Okay, and we know that we need to exceed this delta y greater than 5 meters in order for it to make it over the fence. Okay, so which case will we have? Well, let's take a look. Let's throw some data into our table. This is the first time we've really used the table to any extent. The other ones didn't really require it, but let's go ahead and make this a reasonable size. All right, so now here's our table, and we're going to start filling some data in. Okay, so we know that x acceleration is 0, y acceleration is negative g. Those are alwayses. That's not a real word. Those are always true. So for x, we have a delta x of 124 meters from the problem. We have a y that we want to know. We want to know what y is, and the question is delta y greater than 5 meters, right? Will it clear the fence or not? All right, we know v naught for x is going to be v naught cosine theta, and for y, it's going to be equal to v naught sine theta. With this, I don't have it on this chart, but it's convenient to put up here what our initial conditions are. V naught is equal to 37 meters per second, and theta is equal to 35 degrees. That'll help us when we figure these things out down here later. Okay? V final, don't know, don't care, and time is what we're going to solve for so that we can bridge over to the y direction. Okay, we're actually going to solve for it over here on the x side. Well, let's see how we figure that out. How do we figure that out? All right, what do we have for in the y direction? Let's take a look and compare. The y direction, we have 1, 2, 3 things. That's not enough for us to solve. We need 4. Okay, we need 4, and we need to know 3 of them in order to get our question mark solved. So we're going to have to get that information from what's going on in the x direction. That's what makes it a hits the wall problem. We have acceleration, we have delta x, and we have our x velocity. Remember, we only, for these here, it looks like we only have 3. What are we trying to solve for? Time. Okay, remember that because the velocity in the x direction is constant, we don't even really need to use the acceleration term. All right, what I mean is this. We could say that delta x is equal to v naught t plus 1/2 ax t squared, and then immediately just say, well, ax is 0. And so we'll just say delta x is equal to v naught t. Or we can recognize that since we have a constant velocity, we can just say that v average, whatever, is equal to delta x over t. Delta t, technically, but we're starting at t equals 0. Okay? So either way, we're going to end up with the same thing. Both of these expressions right here will rearrange to give us that time is just going to be equal to delta x over vx. And of course, vx is t is equal to delta x over v naught cosine theta. All right. As I said before, even though I typically prefer you to use expressions and substitute expressions so we're not doing lots of calculating and losing of precision due to rounding, it's really more reasonable with a projectile problem, which are already complex enough, to go ahead and solve for that. So let's just go ahead and say that t is equal to 4.9 seconds, and we won't get all bent out of shape about that. So let's go ahead and put that up in here, 4.09 seconds. In fact, let's write it legibly, 4.09 seconds. All right, so time is the bridge, so now we have 4.09 seconds for motion in the y direction as well. In other words, time is going to be constrained by how long it takes the baseball to go from here to here, which we just decided is this distance divided by its horizontal speed. And in that amount of time, the baseball will be going up and then maybe coming down, but we want to make sure that when it goes up and comes down, that it ends up at some place greater than 5 meters above where it started. In other words, we're talking about a delta y greater than 5 meters. That's what we want to know. If it's less, it won't clear the fence. If it's more, it will. All right, so now taking a look at what we have in the y direction, we're trying to solve for delta y. What do we have? We have time. What do we need to have in our equation? We need to have time. We have v naught. We need to have delta y, and we have acceleration. If you take a look at those four things, hopefully by now you're comfortable with the idea that that will be the meat grinder equation. So now we're going to say that delta y is equal to v naught y t minus 1/2 g t squared. Notice I've already got things set up for stuff going on in the vertical direction. We've got a delta displacement called delta y. We have the y component of the initial velocity, and we have the y acceleration, negative g. All right, so now what we're going to do is we're going to plug in these numbers, and once we plug in numbers, we'll get delta y is equal to v naught y. V naught y is v naught, not numbers yet, v naught sine theta times t minus 1/2 g t squared. All right, that one last thing. Now we can put the numbers in. We're going to get delta y is equal to, what's our initial velocity? 37 meters per second times the sine of 35 degrees. We're going to multiply that by 4.09 seconds. I'm going to run out of room here. I'll make this a little smaller, huh? 4.09 seconds, and then from that we're going to subtract 1/2 9.8 meters per second squared times 4.09 seconds quantity squared, and taking a little time to put it in our calculators, what we end up with is delta y is equal to 4.8 meters. And we needed 4.10. I mean, we needed 5 meters. Okay, so this is going to end up 2/10 of a meter short of clearing the fence. Okay, so does not clear the fence. Make sure you answer the question that's being asked. Does not clear the fence. Okay? For those of you that are interested in a treatment that is strictly algebraic, not substituting 4.09 seconds, just putting in algebraic substitutions and then putting in numbers in at the very end instead of the old Texas two-step here, I will do that, and I'll call it problem 3B, algebraic substitutions, and you can look at that video if you want. And okay, there it is.